The second law of thermodynamics, and engines of cognition, Part 1. The first law of thermodynamics, better known as conservation of energy, says that you can't create energy from nothing. It prohibits perpetual motion machines of the first type, which run indefinitely without consuming fuel or any other resource. According to our modern view of physics, energy is conserved in each individual interaction of particles. By mathematical induction, we see that no matter how large an assemblage of particles may be, it cannot produce energy from nothing, not without violating what we presently believe to be the laws of physics. This is why the U.S. Patent Office will summarily reject your amazingly clever proposal for an assemblage of wheels and gears that cause one spring to wind up another as the first runs down, and so continue to do work forever, according to your calculations. There's a fully general proof that at least one will must violate our standard model of the laws of physics for this to happen. So unless you can explain how one will violates the laws of physics, the assembly of wheels can't do it either. A similar argument applies to a reactionless drive, a propulsion system that violates conservation of momentum. In standard physics, momentum is conserved for all individual particles and their interactions. By mathematical induction, momentum is conserved for physical systems whatever their size. If you can visualize two particles knocking into each other and always coming out with the same total momentum that they started with, then you can see how scaling it up from particles to a gigantic complicated collection of gears won't change anything. Even if there's a trillion quadrillion atoms involved, 0 plus 0 plus 0 equals 0. But conservation of energy, as such, cannot prohibit converting heat into work. You can, in fact, build a sealed box that converts ice cubes and stored electricity into warm water. It isn't even difficult. Energy cannot be created or destroyed. The net change in energy, from transforming ice cubes plus electricity to warm water, must be 0. So it couldn't violate conservation of energy, as such, if you did it the other way around. Perpetual motion machines of the second type, which convert warm water into electrical current and ice cubes, are prohibited by the second law of thermodynamics. The second law is a bit harder to understand, as it is essentially Bayesian in nature. Yes, really. The essential physical law underlying the second law of thermodynamics is a theorem which can be proven within the standard model of physics. In the development over time of any closed system, phase space volume is conserved. Let's say you're holding a ball high above the ground. We can describe this state of affairs as a point in a multidimensional space, at least one of whose dimensions is height of ball above the ground. Then, when you drop the ball, it moves, and so does the dimensionless point in phase space that describes the entire system that includes you and the ball. Phase space, in physics speak, means that there are dimensions for the momentum of the particles, not just their position, i.e., a system of two particles would have 12 dimensions, 3 dimensions for each particle's position, and 3 dimensions for each particle's momentum. If you had a multidimensional space, each of whose dimensions describe the position of a gear in a huge assemblage of gears, then as you turn the gears a single point would swoop and dart around in a rather high-dimensional phase space. Which is to say, just as you can view a great big complex machine as a single point in a very high-dimensional space, so too, you can view the laws of physics describing the behavior of this machine over time, as describing the trajectory of its point through the phase space. The second law of thermodynamics is a consequence of a theorem which can be proven in the standard model of physics. If you take a volume of phase space, and develop it forward in time using standard physics, the total volume of the phase space is conserved. For example,
let there be two systems, X and Y, where X has 8 possible states, Y has 4 possible states, and the joint system, X, Y, has 32 possible states.
The development of the joint system over time can be described as a rule that maps initial points onto future points. For example, the system could start out in X7 Y2, then develop, under some set of physical laws, into the state X3 Y3 a minute later. Which is to say, if X started in 7, and Y started in 2, and we watched it for 1 minute, we would see X go to 3 and Y go to 3. Such are the laws of physics. Next, let's carve out a subspace S of the joint system state. S will be the subspace bounded by X being in state 1 and Y being in states 1 to 4. So the total volume of S is 4 states.
And let's suppose that, under the laws of physics governing X, Y, the states initially in S behave as follows.
X1 Y1, greater than X2 Y1. X1 Y2, greater than X4 Y1. X1 Y3, greater than X6 Y1. X1 Y4, greater than X8 Y1. That, in a nutshell, is how a refrigerator works. The X subsystem began in a narrow region of state space, the single state 1, in fact, and y began distributed over a wider region of space, states 1 to 4. By interacting with each other, y went into a narrow region, and x ended up in a wide region, but the total phase space volume was conserved. 4 initial states map to 4 end states. Clearly, so long as total phase space volume is conserved by physics over time, you can't squeeze y harder than x expands, or vice versa. For every subsystem you squeeze into a narrower region of state space, some other subsystem has to expand into a wider region of state space.
Now let's say that we're uncertain about the joint system, x, y, and our uncertainty is described by an equiprobable distribution over S.
That is, we're pretty sure x is in state 1, but y is equally likely to be in any of states 1 to 4. If we shut our eyes for a minute and then open them again, we will expect to see y in state 1, but x might be in any of states 2 to 8. Actually, x can only be in some of states 2 to 8, but it would be too costly to think out exactly which states these might be, so we'll just say 2 to 8. If you consider the Shannon entropy of our uncertainty about x and y as individual systems, x began with 0 bits of entropy because it had a single definite state, and y began with 2 bits of entropy because it was equally likely to be in any of 4 possible states. There's no mutual information between x and y, a bit of physics occurred, and lo, the entropy of y went to 0. But the entropy of x went to log 27 equals 2.8 bits. So entropy was transferred from one system to another, and decreased within the y subsystem, but due to the cost of bookkeeping, we didn't bother to track some information, and hence, from our perspective, the overall entropy increased. If there was a physical process that mapped past states onto future states like this: x2, y1, greater than x2, y1. x2, y2, greater than x2, y1. x2, y3, greater than x2, y1. x2, y4, greater than x2, y1. Then you could have a physical process that would actually decrease entropy, because no matter where you started out, you would end up at the same place. The laws of physics, developing over time, would compress the phase space. But there is a theorem, Liouville's theorem, which can be proven true of our laws of physics, which says that this never happens. Phase space is conserved. The second law of thermodynamics is a corollary of Liouville's theorem. No matter how clever your configuration of wheels and gears, you'll never be able to decrease entropy in one subsystem without increasing it somewhere else. When the phase space of one subsystem narrows, the phase space of another subsystem must widen, and the joint space keeps the same volume. Except that what was initially a compact phase space may develop squiggles and wiggles and convolutions, so that to draw a simple boundary around the whole mess, you must draw a much larger boundary than before. This is what gives the appearance of entropy increasing. And in quantum systems, where different universes go different ways, entropy actually does increase in any local universe. But omit this complication for now.